Absolutely. Then let me repeat that one vision, the part of the vision statement, and that is that Resonate is going to be a globally distributed, infinite event loop. And an event loop is the heartbeat of our systems. And if you look, for example, in JavaScript, it is the event loop that schedules a function for execution. The function takes a step, the function calls another function represented as a promise, and then the function suspends itself. And then the other function will take over. And this coordination happens on an event loop, right? The event loop is the one that coordinates and schedules the function to take another step and then drives them to execution. Now, if you think about this and lift it one level, lift it into the cloud, our cloud applications are typically event-driven applications. But writing event-driven code is, this is my personal opinion, but is hard and almost terrible, right? But once again, let's look at JavaScript, right? So first JavaScript was callback style, right? And writing callback style was terrible, especially if you had complex control flows and loops. But then now you have async await. But what is async await? It lets you write code, sequentially looking code, but that code is executed concurrently by the event loop. And now I want to do the same. I want to be able to let you write sequentially looking code, but that code is executed in an event-driven manner, executed by the or composed, coordinated by the event loop. And now you have truly distributed, true cloud applications, but that that look like normal functions and promises. So that is the underlying vision of Resonate. And it is based on open standards, like, for example, the durable promise is an open standard. It's an MIT license. Anybody can implement it. And any system that speaks that protocol, and the protocol is very simple. Any system that speaks the protocol can coordinate with any other system that speaks that protocol.
One question here. The very first time I heard about the durable promise was on your Twitter timeline. And the very first time I read the paper was when you published it on the GitHub repo. So is the paper, is the concept came out of Resonate, or is it coming out of a university? But when you say license, you guys are licensing it, right? You came up with the concept.
Yes, we came up with the concept, we came up with the standard. So I can only claim it to be an open standard in the terms of the license, but nobody else has implemented it yet. Even we haven't fully implemented it yet because we are so early into the journey. But anybody can implement it. It is open in that regard. It is not open yet in the regard of there are many different implementations. They're not. Even our implementation is very, very early. But if you want to implement it, we don't have any any rights to it, right? So it's we released it. We completely released it. We say it's MIT. Anybody does anything with it that they want to. But with that, what we did.
That being said, if I want to implement it, I would want to implement it with you guys rather than taking it and doing it something, because that way I can learn from the masters.
Oh, thank you. We are also on this learning journey, right? So it's like today, later today, we're gonna tweet about Resonate now building in public. So we're gonna turn the visibility on each and every of our repos public. Everything is very much work in progress. So there is a big disclaimer, and it's not only work in progress on the implementation side, but even on the design side. We're trying to learn together. But the very early prototypes, they are incredibly encouraging. So for example, we built the TypeScript SDK, and that TypeScript SDK, a function can await a durable promise. Now, that durable promise can either be implemented by another JavaScript function that runs alongside the caller, just like normal JavaScript. Or the durable promise can be implemented by another system, even from another technology stack. So for example, if you expose an Airflow workflow as a durable promise, then the JavaScript function can await, and I'm actually saying await, the JavaScript syntax, await an entire Airflow workflow, however long it takes, if it runs for a few minutes or if it runs for an hour, however long it takes. And then when the workflow completes, the JavaScript function will take the next step. That's a durable event loop. And that is all based on open promises. On open standards. If you want to commit to that standard, you do not commit to our tech.
Now, there are 3-4 things that I am looking at. For let's take an example of Airflow, since that is the example that was given. In temporal, I have worked extensively with temporal. So your complaints with temporal are justified.
It's solid technology. I worked at temporal for two years. Yeah. So it's like, but in these 2 years, I have seen things that I would have done differently. Therefore, I'm working on that.
Yep. By the way, I know you from temporal days because the idempotency, I had a problem with idempotency, and we had a long chat about that. And you said that your presentation about that. That was the very first chat that I had with you in professional capacity.
That's right. Yes, I was also. It's like I knew I know you. And it's like, but I did not know as I was temporal. Okay, that makes total sense. Yeah.
Yeah. So on temporal, whenever I want to in my team, whenever I want to explain somebody to temporal, I say that, okay, do you know React? Do you know Redux? What temporal has done is taken the Redux on the backend, built a Redux on the backend. I don't know if that is, but that gets people very quickly started into state machines and everything. So what temporal is doing is basically is a distributed state machine, a reliable distributed with state that is maintained in backend. Now, durable promises, you need to maintain state. How are you guys handling that? For example, my worker goes down and I am doing just async run. We need to maintain a registry of some sort of, this is the state of this particular workflow, or this function has been called. This function needs to call that other function. And now we need to know the next function, that there needs to be some sort of registry, something like that.
Correct. This is where we get into the nitty-gritty details, and this is a challenging part when it comes to the implementation. So for the durable promise, the first thing we implemented is a durable promise server, which is basically a special purpose database that handles durable promises. But that is also in detail, right? If you look into the detail, that is also a fairly complex implementation, because we need to guarantee linearizability. We never lie to you. When we say that a promise is resolved, it is resolved. Nobody else will ever have a chance to observe the promise as not resolved but rejected, for example. When you hit the timeout, we guarantee that the promise will be timed out, right? Nobody else will ever be able to observe the promise being in a different state, and so on and so forth. So that is a very big, actually, we have the especially when we take idempotency into account, we have a state transition table of, I believe, 60 different transitions that are meticulously tested and implemented to make sure that the server is absolutely rock solid. That is the very first step. But
at this particular point in time, I have a question. I have looked at the implementation. I don't see that, okay, if a server is currently a single worker, you guys have tested it as a single worker, or there are multiple workers that can sit on different machines in Kubernetes like that, or
so currently the worker is the server is a single node.
okay.
So it gets its scalability and reliability properties in a production setting from you sitting on top of what's it called, Postgres. However, there is a big difference to, for example, a system like Temporal. System like Temporal is a cluster, but that cluster acts as one, right?
Yes.
For durable promises and the durable event loop, you do not have to act as one. That's very important because I want that openness. You can connect to one durable promise server and you can connect to another durable promise server. That is very important when you want to, for example, connect to your own code and logic that runs on top of your own durable promise server. But also if you want to connect, for example, to Airflow, and Airflow itself exposes itself as a durable promise, right? Okay. So that means that a durable promise is not, your application is not tied to a single cluster. Your durable just like web pages, right? One web page can link to another web page regardless where it is hosted. Doesn't have to be hosted on the same domain. It doesn't have to be hosted on the same node. It doesn't have to be hosted on the same web server. This is truly distributed. The durable promise has a URL wherever that thing is hosted, doesn't matter. Therefore, also the scalability is similar. The scalability properties are similar to web scalability in that case.
Can I disagree with that? My question is, can I disagree with your statement?
Always. It's like, please. Yeah? And I also know a few edge cases, or not edge cases, I know scenarios where that is still a challenge. Yes.
Before I can challenge your statement, I want to clarify a couple of things. Number one, the state is being maintained by a Postgres server.
Yes. Mm-hmm.
And one worker against one Postgres server. No two workers will be treated differently by resonate async durable promises.
I did not fully understand that question. Let me say it differently. If you have your code running, so let's call your code the worker code, right?
Yes.
This is an end-to-end relationship. Your code can connect to as many durable promise servers as you want, and the durable promise servers, as many workers as one can connect to them. So it's an end-to-end relationship.
The way I understand was durable promise server, there can be only one durable promise server against one database.
Against one database, yes. Mm-hmm.
What if the durable promise server goes down?
In that case, so far, our entire scalability and reliability strategy relies on the scalability and reliability strategy of the underlying database. So you need to host the database scalably and reliably. However, that is on the roadmap. Don't get me wrong. That is on the roadmap that the worker itself. The server itself is gonna get an application level scalability and reliability story. But we are not focusing on that right now. I don't want to be cocky because this is very difficult. Don't get me wrong. Yes. But on the other side, we also know like how to do that. But there is a lot of things we don't know about a globally distributed event loop. So we are focusing on the globally distributed event loop first. And
Okay.
again, it's a very difficult problem, and I don't want to be cocky, but it's also a problem that that has, let's say, a lot of examples and a lot of patterns available to be tackled. Yeah. So we want to make sure we tackle the unknown first before we tackle the unknown knowns. Or known unknowns. Yeah, exactly. Mm-hmm.
Yep, makes sense. The third question is, actually that question doesn't answer, is not answered. The third question was that, okay, the promises, each promise is identified by an idempotency key. So if there is a new idempotency key, there will be a new promise. It will be identified. The ID field in the database is probably the idempotency key.
So the promise has an identity. That identity is unique. Now, operations on the promise have idempotency keys. So that our server is able to deduplicate if a client retries an operation. So the identity itself is already that makes sure that there is not two identical promises. And the idempotency keys make sure that we can deduplicate on the operation. What that means is that
how do you define an operation?
For example, create promise or then resolve promise. These are the operations that we have. If a client sends, let's say the promise is pending, the client sends a resolve promise with idempotency key 1, then the server will transition into the promise is resolved state. If the client retries that operation with the same idempotency key, the server will signal, I did it, even so it didn't do it again, right? But if the client retries that operation with a different idempotency key, the server will say, because that already happened. So it's basically just a huge state machine to make the retry logic on client distributed system. You always have to retry, right? To make the retry logic on clients absolutely smooth, but also ensures that you are never able to, we will never lie to you. You're never able to observe something that later on we will go back on our words. Otherwise, the developer experience is just terrible, right? So it's like,
yeah. So operation is create promise and reject promise, and then if we take temporal as an example, everything, every function run which has an idempotency key, every function run will have its own idempotency key. So, but every function run, if I am correct, can call another create or delete operation.
Correct. Yes, correct. You can infinitely nest this. One function calls another function, calls another function, calls another function, infinitely nested. And you can also do other things. It's a first-class citizen. So for example, if you look at temporal, a workflow creates an activity. So that workflow can wait on that activity. No other workflow can wait on that activity.
Yes.
In JavaScript, when I have a handle to a promise, I can start 10 other function executions, give them that promise as a reference and say coordinate with that as well, right? So now you can do the very same thing with durable it's a first-class citizen. It's just a normal, it's functions and promises all the way down. Even so, it's durable functions and durable promises. Durable functions, durable promises all the way down. However you want to build your application.
That is a very interesting way of looking at it. Now, my question regarding, and I understand because I have read the paper and I have also gone through the code and I have given tried the server with curl commands that this is happening. So that probably helped. Your explanation probably along with that has cleared out the concept. Now let's talk SDK. let's say we create a durable promise. In TypeScript, you are doing it by resonate.run that calls a durable promise. And a durable promise can call another durable promise, and it can go on forever. Now, what if we are in 9th or 10th or 11th or 12th state that, okay, one function N1 has called the promise, and now we are executing N12 and the server goes down, and the worker goes down. We come back and there is already a durable execution happening, but there is no handle to it.
There is. You
Okay.
always, yeah, I love it. Exactly. You always need the handle to the durable execution, right?
Yes.
Because that is a prerequisite for restartability. You need this logical identity of a durable execution, right?
Yes.
Because a function execution has this internal identity, and when your runtime goes down, this identity vanishes, right? But the durable execution's identity sticks around. And you know what's so awesome about this? If you look at functions and promises, one function execution is represented by one promise, right? Just in JavaScript, if I call a function, an async function, what I get back for this async function is one promise. Therefore, the identity of that promise is in a one-to-one relationship with that identity of that function. So when we restart, and we have not implemented restart yet, by the way,
Okay.
but we have already designed it and validated it. So the way to implement restart is when we call a top level function, the resonate run, right? That's a top level. That's the entry point. When we call first, and it's really dead simple, yeah. First, we create the durable promise that represents that function execution. That durable promise is now pending, right?
Yes.
When your worker crashes and comes back up, we ask, give me every top level entry point, give me every top level promise that is still pending, because if it was pending, that means it was still in flight. And every single one that was pending, we just restart again. We store the function and the arguments to the function in the promise itself, in the durable promise itself, and then start the function with that again. And that is how you have a handle on the durable execution. Their identity is tied to the identity of the promise.
Okay. Understood. Now, the second question. So supposedly this is we are talking about a globally distributed event loop. That event loop is going to basically the state machine is globally available. That is what I heard from it. Now, let's say we have that one state machine and one server from, and we are designing an edge distribution location or edge distribution for users in Facebook. Awesome. And we are designing also for somebody who's living in Saudi Arabia, and we plan to do this in real time. Now, the handle, both of the workers come at the same time. Now the handle, both will say that, okay, give me all the handles. And now we will have, we can hit an edge case where one promise can have multiple handles, and then we are going to run into issues.
We run into races. Yes, we run into so what we cannot prevent it because it's a distributed system. And somebody could also write malicious code, right? So we cannot prevent that two functions try to resolve a durable promise at the same time. We cannot prevent that. What we can prevent is we will make sure that only one function wins, only one wins. And
how are we going to do it? Because sorry to break you, but without leader election or some sort of consensus algorithm, this is not possible.
Yes, you're correct. But so currently one promise is tied to one server, right?
Yes.
That server provides the linearizability. We guarantee linearizability. Therefore, only one can resolve or reject. And even if the second one tries to resolve or reject with the same idempotence key, even with the same idempotence key, we will signal that it worked, but we will return the result. And I have a nice graphic for that. I share that later with you. We will return the result of the winner. Everybody in the entire world will see the same, guaranteed, will see the same result for this particular promise. Nobody will see anything else. Even if your local computation says, oh, we failed, we want to reject the promise with the same idempotency key, we will overwrite that and say, well, but somebody else resolved the promise with this idempotency key. Therefore, they won. Therefore, you must treat your local computation as if it worked, as if it succeeded. And by the way, this is the return type that you have to use. Everybody else on the entire world sees the same.
Okay, my question is, why would he want to continue the execution? Because
you do not. You do not. Yeah, no. You do not want. So if you figure out that you are in a race, you do not want to continue. You don't. First off, you don't want to race in the first place, right?
Okay.
Second, if you run into an edge case where you do race, right? You do want to stop your execution as soon as you figure out that you are in a race. However, if you continue racing, I don't think we will own every SDK down the road, right? So, and this detection, we can help you on the server, but we cannot force you to stop local computation. The only thing we can do is ensure that you cannot mess anything up. So we will, but you are entirely correct. Any well-behaved SDK must work towards the common goal of not racing in the first place. If you end up racing in an edge condition and you notice you're racing, stop the computation. But if you don't stop the computation, you cannot mess up for anybody else.
Why wouldn't the SDK wouldn't want to continue? Because we should trigger some sort of a error from it, that okay, this is an error, you cannot continue, and whoever is consuming the SDK should handle that exception from the promise.
You are correct. We have two different types of let's call them errors or exceptions.
Okay.
One type of exception is the type that signals that something in the durable execution is going wrong. So for example, I want to charge a credit card. I couldn't, right? That is an exception that we shall present to the rest of the computation, right? So it's like, hey, you're a durable execution, you wanted to charge a credit card, it didn't work. But then there are also situations that are more, let's say, technical. One of those is, for example, we couldn't connect to the durable promise server. The other one is we detect the race. These ones we do not expose to the code of the durable execution. We expose to your worker code, which is like it's a difference in level. So now your worker code gets to handle the fact that something in the durable execution was not able to, like on a platform level, wasn't able to execute. But the durable execution code is completely circumvented. We suspend the entire durable execution.
Got it. Now, on the SDK part, I believe that the very first step of action would be to poll the server and get the status, the very first task the SDK would do is get the status of all the unresolved promises. Give me all the unresolved promises.
Yes, that is the recovery path. The recovery path is, so, okay, now we are getting into another territory, which is the durable execution itself, not the durable promise, but the durable execution itself. There,
Okay.
now the question is, how do you want to implement your durable execution? Do you
Yes.
want to implement your durable execution like temporal? That is replay based, right? You're
Okay.
replaying up to the point where your worker crashed, for example.
Yes.
But there is other possibilities out there. For example, do you want to implement restore or reload based? So you can capture the state of your execution, right? And then rehydrate or reload your execution from where you left off. We support both of these models. Now
Okay.
you can decide which one you want. There is actually a really cool open source project out there, Stealth Rocket, that has serializable coroutines implemented in Golang. So you can run a Golang process and then serialize the entire process to disk. Then when the durable promise executes, or I'm sorry, when the durable promise resolves, you load wherever the process left off. You don't have to replay, you just load and then take the next step. So that which road you want to go down, the replay based or the restore based, affects how your SDK looks.
In durable execution, I don't think the way we are trying to attack the problem, replay is going to be an overkill. I think that, but this is my opinion. Obviously, I can be wrong, and it will be faster to recover because we are just looking at how many executions are remaining. Give me those. I don't care
Fantastic.
about where it came from, and I don't care who your parents were and who your children are going to be. I don't care. Just tell me what to resolve right now.
Good. Fantastic. So there is now we're really getting into the weeds, into the details. So I don't believe in the log personally, right? So it's like I don't use a log. However, some durable execute, let's say, depending on how you structure your functions. So let's say you have a durable execution, that durable execution calls another function, calls another function, calls another function. If you crash down there, you have to basically replay up to, no, it's not replay. You have to restart and then catch up. The thing though is that if you use durable promises, you don't have to use a log because whatever promise is already resolved will just deduplicate.
Yes.
I can show you, I was actually about to write the pseudocode for how we nest durable promises and actual promises. Yeah? We use promises as a memoization device to store progress, basically. And with that, replay becomes very simple, very straightforward, very simple. There are also edge cases when it comes to OR, for example, OR combinators of processes. You have to remember which process resolved first. But you do that once again with a promise, because promises compose. You don't need anything else. You don't need the log. You don't need an event stream. You don't need all of that stuff. All you need is functions and promises themselves compose. There are AND combinators, OR combinators. Yeah? And if you use them, you don't need anything else. But now it's a lot of information.
I take my words back. I do care about where you are coming from and where you are going. Yes. I was wrong because I just remembered how the TypeScript SDK is. What if the promise is within a promise, within a promise, within a promise, just like inception? So in that case, for to get to that promise point, because it's a result of another promise, I do need the parent. I do need a little bit of replay.
But
how are we planning to attack that? With context or something like that?
You know, we are switching our repositories to public today.
Okay.
And I can point you. Oh, actually, I also tweeted about this last week. Give me just 1 second. I can share the tweet. Oh, here. It is the core mechanic. It's actually really straightforward.
For you.
Here we go. It's really the core mechanic are these few lines of code. First, you create the durable promise.
Okay.
If it was already created and already resolved, if you use the same idempotency key, this few lines of code will just say, okay, we already did this, and this is the result. So just return it right away, right? It's basically the fast path. And only if the promise was created, but it wasn't resolved or rejected yet, do we call your code the function. Then we use the value of your code, and try to resolve. If we ran into a race, which we hope we never do, but we cannot prevent it because it's a distributed system, we will always return the value that was already stored on the server. 99.99% of the time, it is the value that we just getting back from your function will be returned. But even if somebody else resolved the promise in the meantime, even if you went in there with a curl command, right, and resolved it like maliciously, yeah, let's do this, we will resolve with the very same. Nobody will ever see a different value. We will never lie to you. Your code will never see anything else. Whether it runs now, tomorrow, in 2 weeks, you will always see the same values, guaranteed. All edge cases in that regard, all edge cases are resolved. And then we'll just return, right? So we use it as a memoization device. We just embed your code between create and resolve. That's all we're doing. And we basically, quote unquote, cleverly deduplicate. And cleverly means 65 different state transitions, something to that effect, of things that could have happened.
That is happening in SDK.
No, these 65 state machines are actually happening on the server. You will never see. This is all you need on the SDK side. It is this code that you need on the SDK side. That's it. Everything else is just packaging this thing up nicely. So, and my very first complete end-to-end implementation was less than 200 lines of code. Okay, the very first one was less than 80 lines of code. And then with error handling, it was less than 200 lines of code. The temporal SDK has 85,000 lines of code. The SDK has 85,000 lines of code.
They have, I can empathize with Summer and Maxim because they have spent 5 years of their life trying to cover different edge cases and doing it. Pressures.
Yes.
They did a marvelous job at that.
They did do a fabulous job. And I always tell everybody who asks, is like, okay, why are you able to do it with less? It's like, number one, I worked at Temporal for 2 years and I had the luxury to study the system for 2 years. Therefore, and like really study the system for 2 years. And that system grew over 10 years of time.
Yeah.
So the only, you know that quote, the only reason, if I see far, then because I'm standing on the shoulders of giants, right?
Yeah.
Because absolutely they did a fantastic job to tackle each and every edge case. And one of the things that I did is basically grabbing the edge cases from the system and pulling them into a small core. That's it. Yeah, that is
Yeah.
that was that, and that was a luxury that Max and Samar simply didn't have because they were the first ones, right? They were the trailblazers. And then I let me see the durable promise. I send you the state transition table alone. Yeah.
Yes,
Here's,
state transition table. I have looked at it.
oh, you
So
saw it, yeah.
it doesn't look like more than 200 to 300 line of SDK code. If But my question is still unanswered. If we How do we plan to uh, know where we are? Because I asked the question, are we doing it through context? Because we need to maintain some sort of a parent, right? This is the parent that is coming
Ah,
in.
I see. I'm sorry, I misunderstood that question. Yes,
Oh,
that is exactly how we did it. So we are threading through a context because
okay.
every time we say context.run, we are basically incrementing a counter.
Okay.
And we are also incrementing a hierarchical counter. So the first promise is, for example, say something, foo.1, and then it's foo.1.1, foo.1.2. And if that one spans another one, it's foo.1.2.1. So this is basically the nicety. We are spanning the context. However, you can also override with your own identifier. That is often the case if you have known business entities. So if you want to wrap, for example, a known AWS SageMaker workflow, and you know the name of it because, hey, we run one of these per day. So we call it foo and the date. Then you can call it foo and the date. And then the system, by the way, will deduplicate. So the system, if 2 or 3 different functions try to run that thing, they will all back up. Only one will run it, the end. If you have globally distributed, then you cannot easily back up on that. Right? Then we need to talk about something like, and we actually plan to include that into our server, locks. Locks that live with the lifetime of promises. As soon as a lock is resolved or rejected, the lock automatically releases because nobody needs to hold it anymore. So locks become very simple.
Lock.
Hmm?
I don't think we need a lock.
You
Lock
do
means
not. Hmm?
lock means a lock will be held by what? Handle?
Yeah, you do not necessarily. You're correct. For correctness, you do not need a lock, but the lock helps you to avoid any simultaneous executions, any race condition. But you're correct. For correctness, you don't need it. It's a nicety that now you can guarantee that if you have a server on the other side of the world, if the server checks on the lock, right, even if the promise is pending, but somebody else is holding a lock, then the server says, well, somebody else is working on it, so I am not going to work on it.
Okay. What if
It's a
the whole
nicety.
what if the lock goes down? Is there a heartbeat between a lock and the worker?
Yeah, exactly. That is the nicety of the lock. The lock lives with, because as soon as the promise is resolved or rejected, the lock can automatically be released. Nobody else in the world needs a lock anymore. Yeah. And but
So no
during
heartbeat,
the
no heartbeat. There is a time to live. That if we don't get a heartbeat in this time, we will release the lock, and somebody else can claim it.
correct. But even there is a fantastic article by Martin Kleppmann. You cannot guarantee correctness with locks. Therefore, our correctness guarantee. Let me share that article. Martin Kleppmann distributed lock. It's a fantastic article. That article leveled me up so much. I think that was my breakthrough article in distributed systems. Then I was like, oh, now I understand. What
Mine
can I do?
was
What can I not do?
GFS paper.
Oh, which one?
GFS, Google File Systems paper.
Oh, okay. Then you know what? Google File System. I will read this paper again. I have read it long time ago, obviously, because it's old. But I have never read it with this like mindset, with this idea that, oh, this is my breakthrough paper. Now I want to read it with fresh eyes. Okay, cool. Got it. Because I noticed that like the breakthrough papers, if you read it with that mindset, it's like you can often see where like people come from. And then it's like, oh, okay, I get it. So it's really cool. So thanks for sharing.
No problem. I will read it in my spare time.
It's a great paper. Great. Yeah. Because it really shows you what can you guarantee and what can you not guarantee. So therefore, when I talk about distributed locking, I always say it's a convenience feature, but you must never base your correctness guarantees on it. So it's only an optimization. Therefore, we have planned a locking feature as a secondary feature for our promise server to make writing SDKs simpler and make systems be more responsive. If a heartbeat is missed, for example, we make them more responsive, but we do not base our correctness on it.
All right. So this. How do you advise me to approach the next step in Go SDK? Should I wait for the TypeScript SDK repo to be available so that I can go through it and
that would be my suggestion. Check out the type, and that is going to happen within the next 2 hours.
okay.
So probably for you, basically next business day. Yeah. So, and then I can point you to some of the magic. I can also introduce you to David, who is the one who implemented the TypeScript SDK and also a lot of the server. And please do feel free to engage a lot on Slack. And then we can think about it's like how to approach implementing a Golang durable executions, because I would argue we're not starting at step 0 for Golang. We're starting at step -1 because Golang doesn't have a notion of coroutines, right? If you look, it fits super well, the whole idea of functions and promises, TypeScript, JavaScript, Python, Rust, C#, Kotlin, Scala, Java, name your poison. But the one thing that says, oh, we don't need functions and promises, we have channels, was Golang. So therefore, even Tempora, right? They need to implement their idea of how does a coroutine look like. We have a coroutine implementation in our backend that we can look at together. Our coroutine implementation is an interesting one. It is concurrent, but not at all parallel. Our server rejects platform level concurrency. We have only application level concurrency. Why? Because we wanted to be able to fully implement deterministic simulation testing. Every single step that our system takes is scheduled by our scheduler, never by the Go runtime. At no point in time in the core of the system, of course not for I/O, that's different, but in the core of our system, at no point in time are 2 Go routines enabled at the same time. That is very restrictive, but it's fantastic for testing. However, we can also implement it differently to say, you know what, a Golang coroutine is basically running in its own Go routine, and it can schedule at any point in time whenever we want to. So that is one of the decisions that would be an early decision.
I'm thinking about durability because I have to come back and sort of replay the state and go that how I'm going to do a replay of that sort here. I don't know, but let me go through let's wait for number one. You mentioned David. Thank you for offering to introduce. We will chat with David if we need to be. Let's treat David's time to be very expensive.
You know, thank you very much. Thank you for that. But we are, again, we consider ourselves to be in the design phase. We
Okay.
really want as much like thought as possible, right? So, and with everything you already said, it's like I will obviously also take that to my team, right? And it's like, listen, it's like we have some good things to think about here, right? And so the more of that, the better, because again, the design, we really want. I believe, and we need to spend more time on the design phase, not less, because any issue we find in the design phase is worth its weight in gold, right? Because
Yep.
again, the right the benefit of hindsight, right? So there's like and I really don't mean to bash Tempo. It's a great piece of technology, but there is a lot of design decisions that cannot easily be undone, right?
Yep.
So I want to make sure that the core is just right. Yeah.
We are going to make mistakes.
We are going to make mistakes. Exactly. That's why we need as much thought upfront as possible.
Yep. Anyways, so the next step for me is I'm going to wait for the TypeScript SDK to come out. In the meanwhile, if you can point me to the concurrency implementation in the current Resonate code, so I can understand where you guys are coming from. And then I will try to think about it something and then come up with a plan that, okay, this is how we feel, and then we can have a design discussion on that. This is what I learned from the TypeScript SDK. This is what I learned from the concurrency implementation. This is what the problem looks like to me right now, and this is how I am attacking it. Probably give me a week or something to go through it.
Absolutely, and I'd be happy to participate and also look basically beyond the durable execution itself into testing. Yeah, how can we test that? How can we so that you just get like a great developer experience with it, right? And I can walk you through if you have any questions on our implementation of the scheduler and the coroutine, because I was already with one like thinking with one. I believe that the way we implemented the scheduler and the coroutine is also capable of implementing the Golang SDK. It has coroutine semantics, and you get your own scheduler, which is basically able, or with that you get full control over the execution semantics, full control over how do we do transparent retries? How do we do transparent rate limiting? How do we do transparent logging and tracing? How do we do transparent observability and metrics collection? And none of that is part of your code. All of that is part of your scheduler, therefore available for each and every durable execution that you ever build.
Yeah, that is
It's quite nice, is it not?
I will have to now look through this scheduler code. Now that
we
I know
implemented that for TypeScript. Yeah.
Now that I know that I can find this is a treasure trove of implementation blasts. So knowledge blasts. So I will definitely look through it and try to learn as much as I can.
Awesome. And I'm super happy to reconnect and also do some design sessions together.
Okay. Same time next week, or we just coordinate on Slack and then?
Either way, whatever works best for you. I am totally available same time next week, or actually, wait, I may have a meeting, but it's like around that time next week.
Okay, we will coordinate on Slack.
Oh, actually, totally available next time this week, next week, same time. Yeah, totally available.
Got it. We will coordinate on Slack and then we will take it from here.
Sounds good.
One thing that I'm in your bucket is to send me the recording of the video when it becomes available so that I can give it to my team.
Absolutely. Will absolutely do.
Thank you.
Hey, thank you very much. And then have a great night.
Same here. Great day.
Thank
Enjoy
you.
Tahoe.
Oh, thank you very much. Bye-bye.